The first speaker is Professor Wada. He's a full professor at the Nana Institute of the Science and Technology, NICE in Japan. He focused on the robot and vehicle control system, human-robot interaction, and the motion sickness modeling. Today, his topic is the modeling the motion sickness towards the comfortable uh, automated vehicle, motion sickness to the motion happiness. So, Professor Wada, please go ahead.
Okay, thank you very much for a kind introduction. So I'm Wada again. I'm very happy to be here and to share my research for you. Okay, so let's start my talk. Okay, so level 3 or higher level of automated driving, which is defined by SAE recommendation practice. A driver becomes a passenger and subtask in the car will be increased. So there is a concern to increase motion sickness. So let's so recall that the original purpose of the automated vehicle is, of course, to release human driver, from driving operation to reduce workload. So and as well as increasing the productivity during transportation. So of course, therefore, the motion sickness should be removed. So so there are around about 7 years ago or something. So many researchers started to mention about their concern. So first one, the pioneering work, Deus and Boss investigate or organize all cause of motion sickness in the context of AD, and for example, sitting backward and the use of IT devices, etc. And also they propose the design guidelines for AVs for comfortable and the productive AVs. And also CBAC of the University of Michigan conducted questionnaire to invest. They asked what kind of activity do you want to do and when the automated vehicle will be available. And based on the result, they estimate the possibility of increased motion sickness. And also, it's kind of advertisement from my side. So I also pointed at that point, this one, emphasize the importance of the vehicle control aspect concerning the motion sickness. So I want to introduce this one in my today's talk. Okay, this slide showed why motion sickness should be considered for an automated driving system for motion design. So you or I, of course, human drivers intuitively consider the ease of driving as well as decrease of motion sickness, right? But it is thought that vehicle motion patterns of AV can be changed dramatically. So and also the computer doesn't know how human gets sick, right? So the motions, therefore, that is a reason why the motion sickness should be explicitly considered in automated driving. Okay, so the quantification of the motion sickness is very important. That is the point today. So there are much effort has been done so far. And the first one is questionnaire to ask the motion sickness, severity of the motion sickness. The second one is biosignal measurement. And third one is computational model. So I focus on that third one. Okay, so there is very roughly speaking, we have two kinds of model of motion sickness. The first one is fitting model to describe the input-output relationship. I mean, experimental result to describe the experimental result, like ISO standard, MSDV or something. And the second one is models that is based on the hypothesis of mechanism of motion sickness, which includes sensory conflict theory and subjective vertical conflict theory. This is a kind of branch of the first one, sensory conflict theory. So, today, I want to focus on the second one. Okay, so let's start my talk. It's the main body of my talk. So sensory conflict theory. It postulates that motion sequence is evoked by the conflict in the sensory information, And the source cause of the conflict is one, modalities of sensory information, such as between visual information versus vestibular information. And the second one is sensory information versus experiences, like memory, or that is described by internal model that is thought we build in our central nervous system. And I believe that second one includes the number one. I mean, phenomena of the number one is can be described by number two, the kinds of number two. Okay. So yeah. Okay. So let me think about what is a conflict. What the definition of conflict in the sensory conflict theory? That is very difficult question. How we can define. Okay, so especially when multiple sources of signal exist. So as far as now I know, there is no theory that deal with the definition of conflict. But only one exception is that this one, subjective vertical conflict theory, in which the conflict is defined by the discrepancy between vertical direction sensed by our sensory organs and estimated ones by experiences formed by internal model. Yes, this is, as I mentioned before, that is sort of built in the central nervous system. So big advantage of this theory is that the multidimensional and multi sources of sensory information can be dealt with. So therefore, the computational model of the SVC theory is actively researched nowadays. And I'm a big fan of this theory. So that's why I'm looking at this theory. Okay, this table shows a very rough sketch of the or big picture of the computational models of SVC theory. Here it's there are many research models, and here is a degrees of freedom, 1 degree of freedom or 6 degrees of freedom or something like this, and how the model can deal with visual flow or visual vertical or prediction, human motion prediction or something like this. So I will present some of them in my talk. Okay, I want to start the very first one. This is a very original one DOF and no vision and no prediction. But this is a very nice pioneering one. Okay, this diagram shows the model. The output is motion sequence incidence, which is defined as a percentage of people who would vomit given by a given motion stimulus. And the input is a very simple one, actual, very slow. My point is not moved. Yeah. Anyway, left hand side, okay, here, actual head movement, only 1 degree of freedom in the vertical direction, like a ship, like this. And they calculate, this model calculate, this OTO means the otolith and sensory organ, and vertical, since the vertical direction is calculated by by using this Lopez filter. And here is what happened in the physical world. And here, these blocks showing that the just copy of them, and this imitates the internal model that is sort of built in the central nervous system. And this is the sensed vertical, and this is the expected vertical direction. And C means the conflict. And the MSI is calculated by using this slow. It's by using this conflict. Okay. Anyway, so this is the 1 degree of freedom. So I expand this model to 6 degrees of freedom motion because I want to apply this theory to the automated domain. Okay. I don't explain more detail about this, but the output is same. The motion sequence is MSI, and we added this one, angular velocity in three-dimensional space, like in pitching, rolling, yawing, or rolling, something like this. as well as three-dimensional head acceleration. And important point is, yeah, this one. Since the particle is calculated by through this kind of blocks, which describes the otolith semicircular interaction. Okay, and here is what happened in the physical world, and the bottom side describes the internal model. And again, this conflict is leads to the motion sickness incidence. Okay, I'm omitting details, so please ask if you have questions. Okay, so we validated our model by using this kind of by comparing with experimental result. The right-hand side is measured motion sickness incidence. They shook the 100 students for 2 hours, and they counted how many people vomited. In 1976, but it's very important research. Okay, the left-hand side shows that the predicted MSI by using our model. Yeah, you can see that our model fits the experimental result very well. And here, yes, both figures have around, okay, I'm omitting detail, but 0.2 hertz here. That is known as the most provocative frequency. Okay. And then now I have model. So we have applied our model to many applications, including analysis of head tilt storage of the driver. And another one is, this kind of personal mobility system. Effect of this kind of tilt function of PMS on motion sickness. So I'm omitting detail. Okay, so recently we're working on adding another or other sensory modalities, including visual, this one, red part, visual information, visual flow. Okay, so we can by this signal is the visual flow, and by using this block diagram, we can simulate or you predict the motion sickness incidence. But if we want to predict the motion sickness by using the experimental data, we need to estimate that signal in some way. So we use the camera image to predict the visual flow by using a very simple optical flow analysis. So I'm omitting detail, but yes, we conducted very small experiments. Participants were exposed to stop-and-go driving in navigator seat. So while they're either looking forward or watching the laptop PC. So this right-hand side shows the predicted method by using my model. So yes, as you can see from this figure, the proposed model successfully described the fact that motion sickness increase when watching the laptop PC. And this agrees with our observation in our daily life, as well as literature. But I'm not too detailed. So I have many things I want to show you. Okay, so this slide shows another visual information, static vision. So I will, this will be presented by our next presentation by Professor Liu. So I'm waiting detail too. Okay, anyway, so this is another final model that I want to tell you. Models capturing the effect of motion prediction of the exogenous motion. So sorry about a very busy slide, but we know that the human can predict, human predictability on the exposed motion affects motion sickness. For example, repeatability of motion sickness, yes, upcoming visual information such as road ahead. I think it's, and also a visual cue or something like this. So as far as I know, no model can describe such effect of motion predictability in passive motion, MS motion sickness. So we have newly developed, we expand to this direction. Okay, this is it. So I'm not in detail, but we added this red part to the boss's original model. In red part, red part described learning and the prediction mechanism of humans. This was introduced here. Yes, I'm not in detail, but we are we compared with the experimental data. So this Voss and Kuiper conducted this kind of experiments. The participants were shaken for about 20 minutes or something for 9 meters. And okay, some in detail, but yeah, in this experiment, predictability of motion was changed. So right-hand side shows the predicted MSI by using my model. Yes, this one. So I'm omitting detail, but predicted MSI in the condition where timing and the direction, both timing and the direction can be predicted. Yes, motion sequence is smallest. So same tendency as the experimental data. Yeah, I need to, okay, so let's get into the final stage, potential application of motion sequence model to the automated driving. I'm a bit in detail, but this slide shows what kind of effort we can make to reduce motion sickness by using a model. For example, yes, motion control, vehicle design, and in-vehicle device, etc. Motion control includes motion planning, vehicle control, suspension system, lean control, something. So yes, yeah, computational model of motion sickness can be used to quantify motion sickness, which means that decreasing motion sickness can be dealt with as model-based optimization problem now, because now we have a model. So I'm omitting the, okay, this, yes, this is it. This is very similar to the slide that I show you in the very early stage of my presentation. But now, yeah, we need to, motion sickness should be explicitly considered in the automated driving. But now, yes, we have model, so we can use that. So I just show you the very small examples. So first one is we conducted this kind of experiment research. First one is a velocity profile generator for automated driving. And another one is a trajectory generator, including the control theory. And also, many researchers have utilized the motion sickness model for deriving strategy to reduce motion sickness. I believe that you will find some research topic in many symposium this year. I believe so. Okay, this is the final slide. So a computational model is promising tool to build a comfortable automated vehicle. So the motion model facilitates to estimate the motion sickness and to turn the effort to reduce motion sickness in the optimization problem. So, but limitation, what we should be aware of is that the phenomenal model can deal with very limited. So, and so we need data. Yeah, right. So data of motion sickness, but yes, data of motion sickness is very important, but it's not easy to get. Okay, so there it means that yes, I want to say that we need to cooperate among researchers. Okay, thank you very much for your kind attention.
Thank you.
Thank you very much. Thanks for your presentation. So does everybody have some questions?
From the on-site or the online, yeah, the online participant can leave your questions in the chat. Also, can ask directly. If there's no question from the participant, I would like to ask a question about the motion sickness things. But I'm not an expert in this area. I just started to read the articles like several weeks ago. But I'm curious about because I know the motion sickness is related to the age. With the young age, before like children, maybe they have more motion sickness than the adults. Like how do you build a model regarding to the different ages, or how do you find a solution to solve the motion sickness problem with the respect to the different ages people? Yeah, this is my easy question.
No, not easy. It's, I think it's very important question, because we should aware of is that there are many models But as you said, yes, the output of the model is motion sequence instance, which means that the kind of group level model. How many people vomit? Percentage who vomit, which means our model is not do not have the ability to describe the motion sequence in individual.
Oh yeah, yeah.
So nowadays, so first of all, we need to change the output of model. Now, several research, including us, are tackling this problem. For example, as I mentioned, yes, here. So nowadays, most trustable method to measure the motion sickness is questionnaire. So, for example, MISC scale or some other things. So nowadays we will change the model, the out of the model to the questionnaire directly, not the percentage who people who vomit. So then we need to change the sensitivity. Okay, so as you mentioned, yes, yeah, there are huge individual difference, the susceptibility of the motion sickness. So after that, so we will tune the parameters of the model to fit the individual. But it's very important and it is very difficult.
Okay, so it needs loads of people to have a lot of data to build a model, like different group of people.
Yeah.
In different ages.
Yeah,
Okay.
yeah, and also the important thing is if we want to have the individual model, we need to conduct experiments for the many times per only one person to identify the parameter of the model. That is a very huge, big challenge for us.
Okay, thank you. Yes,
Yeah,
just for just one.
Okay, maybe I ask a short question. So, as you mentioned that in the last part of your presentation, the data is quite difficult to acquire, I would assume. So, so based on the research you presented, could you tell us how difficult to get like reliable data and also the quantity of data? How can you guarantee how many participants you want to get when you want to have some calculation based on that?
Okay, I think some of them, Professor Liu will answer that your question in the next presentation. But okay, so but yeah, we need to take care of many things to get trustable data, reliable data, because the motion sickness is affected by many factors, temperatures, and how much alcohol they take the last night or something like this. So first of all, in scientific research, yeah, we fix the condition as possible.
Yeah,
that is a big, very important thing.
Okay. Yeah, thank you.
Okay, thank you. So, other questions from the online? I think
So far,
there's a
I think
no.
the participant need some time to like think about it and react.
Mm-hmm. I see. So if there are no further question, I will go to the next speaker.
So I need to turn off.
Stop sharing.
Okay. Yep.
Yeah.
Thank you.
Okay, thank you very much, Professor Wada.
Thank you.
And the next speaker is me. Yeah. Actually, I prepare